protection is a hydrolysis, and that, because these guys are so stable, doesn't work anymore with acid and water. You need mercury too. Mercury turns out to bind to sulfur in thiols extremely well, so it facilitates, it's thiophilic. It facilitates the hydrolysis. So again, it's a Lewis acid, particularly using mercury, so mercury chloride. So what you need is water and mercury chloride. The rest of it is just buffering with a little bit of carbonate, and this is the solvent acetonitrile. You don't need to know that, but water and mercury chloride deprotect. So again, we have protection, deprotection. Now it's a thioacetal. And we'll see more of this later of how these guys can be useful. At the moment, I'm just giving it to you as an addendum, an extension of the oxygen-based systems. This also works with sulfur-based systems. There's one added twist, however, namely these thioacetals and other thioethers, when you treat them with nickel, and this particular nickel is called Raney nickel, which is particularly good at this. It's nickel made by taking an aqueous solution of nickel salts, like nickel chloride and the like, and then reducing it, and this generates a black nickel powder that precipitates, and which got the name after the inventor of this particular method, Raney nickel. You don't have to remember Raney, but it's nickel, even better, nickel and hydrogen, but nickel alone will do it. You just boil it up, and this nickel metal loves sulfur, and it will rip out the sulfur out of organic molecules to make nickel sulfide. So that's a pretty brutal reaction, really, overall. But in a way, it does this very cleanly. And so it pulls out this sulfur and this sulfur, turns this into ethane, and this carbon turns into CH2. So this is another method for, in a two-step sequence, from here to here to here, of removing the carbonyl function. Remember, we did this already with the Clemmensen reduction, zinc amalgam reduction. Did the same thing. You can get rid of a carbonyl if you don't want it. Meaning that retrosynthetically, you can look at any hydrocarbon and put a carbonyl anywhere you want, because you know how to get rid of it in the last step. And placing a carbonyl strategically somewhere, as we shall see this week and next week, is extremely useful, because the carbonyl facilitates all kinds of carbon-carbon bond forming reactions. So that is a good reaction to keep in mind. We'll see a lot of this in chapter 23. Okay, so 3 pieces of vocabulary. Now a little aside. Acetals are not only useful for synthetic organic chemistry, they're useful in all kinds of applications, and nature uses them all over the place. But here's a medicinal application. Medicinal chemists often encounter the problem where a drug, when administered, is metabolized too fast. When you take a drug or any other foreign substance into your body, the first thing that happens is called the first pass. It goes through your liver. The liver is like a waste management company. It's a giant cleanup factory, and it gets rid of what it considers as crap that shouldn't be in your body. And all foreign substances are crap as far as the body is concerned. So all drugs that are artificial, the body wants to try to get rid of them. And the liver is very efficient at this. So many drugs that you take, immediately after the first pass, 20, 30, sometimes more than half of the stuff is thrown out. So it never reaches the intended target. So this is the case in this particular compound here called resveratrol. And I just picked this because this is a very recent paper in Molecular Pharmaceutics where they used the acetal modification. So this is a strategy where medicinal chemists say the drug itself is not readily bioavailable, as they call it, because it gets metabolized too fast. So let's slow down this issue. Let's turn it into what's called a prodrug. Or it really should be called pre-drug, but they call it prodrug, where it's modified such that with a modification that at physiological pH will slowly release the actual drug. And acetals are perfect for this because they hydrolyze at physiological pH, mild acid. And so modification of a drug that contains hydroxy functions or carbonyl functions as acetals is a standard strategy for medicinal chemists. So in this case, what they did is they turned this molecule, which is metabolized in the liver very rapidly, into the tris acetal. Notice that all the OH functions are part of an acetal structure. It's an acetone acetal, where the other half is derived from methanol. So it's a mixed acetal, methanol on one side and the phenol OH of the benzene rings on the other. This guy then allows controlled time-release delivery, ensuring a constant supply over the lifetime of the dose that you've been taking. Now, why did I pick this one? This is actually a very amusing molecule. It came into the limelight, I don't know, about 7, 8 years ago now, because it, for a variety of reasons. But one thing that people found was that it prolongs the life of a number of species tremendously. And we're all into, not all of us, but the internet is full of it, and a lot of people are very interested in living forever. Okay? So, and aging is a major issue for a lot of people. And it turns out that this molecule, when consumed, evidently, or given to, to lab animals, it mimics the effect of a diet, of dietary restriction. And that is well known, including humans, that a good diet, a limited diet, where you don't stuff yourself every day and you take vegetables and fruit and all that, prolongs your life, apart from general well-being and all that. And it mimics that scenario. So this is marvelous, really, that you take a compound that mimics the effect of restricting your diet. And it has other effects, lifespan extension, which is related to restricted diet and exercise, but also improvement in functionality in aging, protection of the cardiovascular system, anti-inflammatory, so that's good for arthritic conditions, and cancer chemo prevention. So here's a picture from the web where this lady before she looked like this, before she took resveratrol, and now she looked after she looked like that. Okay. You're too young to even see the difference. At my age, you can notice immediately. Okay, this is she's got wrinkles, all that, so this is a much cleaner face, sort of Botox kind of effect. What is most amusing is this compound, resveratrol, is found in grapes, red grapes especially, but also white grapes. It's actually an antifungal. It protects the grape from invading fungus organisms. And red wine has quite an astonishing concentration of this fact. And when it was discovered that this compound mimics the effect of a healthy diet, it was used to explain what has always been known for decades as the so-called French paradox, namely that the French eat what other nations consider a rather rich diet, starting with foie gras and then, filet mignon and so on, all the good stuff. And yet the incidence of, that they live comparatively longer, and the incidence of cardiovascular ailments and so forth is lower than in other nations. And people are really pissed off at this, right? Because why could they eat so much and we can't, because we'll die of it. And it was ascribed to be due to the fact that the French, while they're eating all this rich diet, also consume large amounts of red wine, which contains a lot of this stuff. So whether this is true, there have been no clinical trials that plan on testing this. And in fact, whether these effects, which have been tested mainly on lab animals, apply to humans is also, the jury is totally out on that. That doesn't prevent, of course, enterprising spirits to put the stuff and sell it. Okay? So if you dial resveratrol or Google it, and the page comes up and you'll see the bottles, okay, and your images for resveratrol, you can buy it on the web. So I would say be careful with this stuff because nobody knows whether it works on humans, and then nobody knows what potential side effects are when you take this in such large quantities as some of these people do. So here's an application that applies to medicinal chemistry. All right, so we have water and alcohols. They're both related in their chemistry. And as we have done already in chapter 6, when we move from along the periodic table with various nucleophiles, we will often, in the remainder of this course, move from oxygen to nitrogen. The two are very similar. Both are nucleophilic, oxygen much less so because it's much more electronegative. Nitrogen is sort of the nucleophilic brother of oxygen. Nitrogen holds on to the electron pair much less strongly, and therefore amines are basic. The proton will set up, the protonation is relatively easy, and we'll discuss that in a separate chapter dealing with amines. But we already noticed the good nucleophilicity of amines in chapter 6, where we use them as nucleophiles to do SN2 reactions. Okay? So that turned a haloalkane into an amine, something that we'll discuss or remind you of when we talk about amine syntheses in chapter 21. So not surprisingly, amines will add to carbonyl compounds. Okay? They are bona fide nucleophiles. All nucleophiles, in principle, can add to the carbonyl carbon. Okay? So in that sense, the delta plus of that carbonyl carbon is like, and this may be a useful way to think about it, it's like a haloalkane carbon, which is also delta plus, and it attracts nucleophiles. There we're doing an SN2 reaction most of the time. Here, we're sort of doing an SN2 reaction, except that the leaving group is an electron pair that's being kicked out onto oxygen. So the analogy is compelling. If you use that, then you realize, hey, this is really nothing new. Okay? This is what I would expect. It's an extension of what I already know. Okay, so amines add, and there are two types of amines that will add productively. One type has two hydrogens left over on the nitrogen, so this includes ammonia, which has no alkyl whatsoever, and primary amines, where we have one alkyl group, and there's still two H's. And the remarkable thing is that when you treat a carbonyl compound with a primary amine or ammonia, where R equals H, they get together and give what's called an imine, where the CO double bond has been turned into a CN double bond. Quite incredible metathesis is what I call it. Okay? This occurs at mild pH 4 to 5, and the other product is water. And reactions that produce water by carbon-carbon bond formation are often called condensations, or condensation reaction. That's a colloquial term. You can remember this or not, it's irrelevant. But water is being kicked out. Okay? This is a reaction that's reversible. Again, excess water drives it to the left. If you put some desiccant on the right, often molecular sieves or something that will pull out water, it drives it way to the right. And this is a reaction that also nature uses extensively when it wants to convert the relatively reactive carbon-oxygen double bond into something that's slightly less reactive, slightly less blue on this carbon, replacing oxygen with nitrogen, okay? Intermittently, in order to do whatever it needs to do in a particular process. Okay? It's a very powerful transformation. So in a way, an imine is a masked carbonyl, or carbonyl is a masked imine, whichever way you want to look at it. So whenever you see a carbonyl, think of it as potentially imine, and an imine as potentially a carbonyl. So here's an example. Here they took in the literature acetone with cyclohexanamine. Here they used a pinch of HCl to do this. 95% of the CN double bonded species. So this is somewhat bizarre. How does this work? And you will see that the first step is actually completely analogous to the reaction with an alcohol. Namely, there we got a hemiacetal. We get the nitrogen analog of this here, which is called a hemiaminal. And so how does this work? There's a slight difference. You don't need to activate the carbonyl in order for this to occur. The amine is now nucleophilic enough that even without protonation of the carbonyl, it will attack. And so the amine attacks, kicks out the electron pair. This is sort of our pseudo SN2 reaction, where the leaving group is the electron pair. And since we're starting with a neutral species, you get a plus charge of nitrogen, and the oxygen is negatively charged. You get so-called zwitterine again, a dipolar structure. This is now slightly acidic. This is strongly basic, so the proton comes off and jumps over to the OH. And here is our nitrogen analog of an acetal, of a hemiacetal, namely the hemiaminal. The addition product of RNH2 across the carbonyl, proton here, here's the amine. Now, in the case of alcohols, it would stop here unless we added acid to turn it into an acetal. Well, this one doesn't. And the reason that it doesn't is because, unlike oxygen, now imagine oxygen here, which is divalent, the amine still has a proton sitting there. And it's a proton next to a hydroxy in a polarized situation that eliminates water like a shot. Okay? And the elimination of water, that's like the typical elimination of water that we've seen previously to make alkenes. Well, in this case, it makes the CN double bond. And the water is eliminated, often helped by a pinch of acid. This is why often a little bit of acid is added. This is why pH 4 to 5, slightly acidic, helps. But in fact, this will work even without adding anything. The glass walls of your Pyrex vessel, the silica, are acidic enough. There are silicon hydroxy functions sticking out on the surface of glass that are slightly acidic. We'll do this. So protonation here turns into a leaving group. The leaving group leaves, and it leaves in a hurry because what it's making is a carbocation that's stabilized by resonance. Here's an octet structure. Okay? And so then, looking at this, you can see that the proton can leave and generate the imine. Okay? And the hydrolysis is exactly the reverse. You protonate first on nitrogen, then you add water here, deprotonate, and then you go backwards every step of the way back to a starting material. So again, let's look at intramolecular cases. In all of these reactions, I forgot to mention that intramolecular hemiacetal formation, intramolecular acetal formation, and now intramolecular imine formation, where we have reversibility, the best cases for intramolecular reactions are 5 and 6 membered rings because they have the least ring strain. If you go to 4 and 3 membered rings, they're too strained. The reaction becomes endothermic. It won't go. It won't close. So this is a scenario where we have equilibrium situations where the strain rings don't form. This is different from, if you go back to chapter 9, the intramolecular Williamson ether synthesis, where we used an alkoxy halide, and we did an intramolecular SN2 of the alkoxide on the halide. There we noticed 3 membered ring formation, oxocyclopropanes, are the fastest because of the proximity effect. Those reactions are not reversible because the leaving group is a lousy nucleophile, typically a chloride or a bromide. They don't come back and reopen. Okay? So the molecule, in a way, it's a kinetic control. The molecule is stuck with forming the strained ring, and it does that actually rather rapidly because the transition state is low line. So there we know this 3-membered ring is fastest, then 5, then 6, then 4, something like that, right? Here, because it's reversible, thermodynamics control it. So the ring strain does come in. So even though closure to a 3-membered ring in an amino aldehyde or ketone may be fast, the equilibrium lies on the wrong side. So these, however, work nicely from left to right. And so here's a cyclic 5-membered ring imine. Here's a cyclic 6-membered ring imine. So this only works, of course, imine formation if your amine has 2 protons. Because remember, those 2 protons get together with the oxygen, just topologically, of the carbonyl to make water. If there's only 1 proton on the amine, something else happens. And we'll do that after the break.
In the reaction of a ketone with the primary amine, following the last step, the elimination of
So here we are, hemiaminals. There's no proton left, and so water loss occurs to the carbon side of the system. So look at an example here, 3-pentanone with this secondary amine. I'm picking a cyclic one just for added variety. This thing will add the usual way. Nitrogen adds to the carbonyl function, and proton goes on oxygen, the standard addition. And now you notice we can't eliminate to make an imine. And so elimination occurs to the carbon side if there's a proton on the carbon side, of course. And if this is an unsymmetrical system, you get 2 alkenes. Okay, so this is standard alkene or dehydration chemistry to alkenes. And the only difference or twist is that the alkene is an amino alkene. Okay? And they're special, these enamines are special because the nitrogen is an electron pusher, just like the amines are electron pushers to benzene rings, which are 3 double bonds. Here's a single double bond. Okay? And this goes extremely effectively in 90% yield. So how does this go? In detail, here's the mechanism. The amine adds directly. You get these zwitterine. The proton comes off, goes onto oxygen. So here's the removal